You are being lied to. Not by me, not by scientists, but by every alien movie, every science fiction novel, every UFO documentary you've ever consumed. They all promise the same thing. Contact is coming. They're out there. They'll arrive any day now. But here's the truth nobody wants to admit. They're not coming. And by the end of this video, you'll understand why the universe has built an impenetrable prison around every civilization that's ever existed. If you're curious about our place in this grand universe and want to explore the deepest questions science can ask, make sure to hit that subscribe button and give this video a thumbs up. Now let's get started. Most people assume we haven't found aliens because they don't exist. But what if the truth is far more humbling? What if they exist? But the universe itself has built walls so high, so insurmountable, that even the most advanced civilization in the cosmos can't overcome them. Let me paint you a picture. The Milky Way galaxy, our cosmic home, contains somewhere between 200 billion and 400 billion stars. That's not a typo. 200 billion. If you tried to count them, one per second, it would take you over 6,000 years. And that's just our galaxy. The observable universe? It contains approximately 2 trillion galaxies. Do the math, and you're looking at more stars in the universe than grains of sand on every beach on Earth. Every single grain. Multiply that by thousands. Now we've discovered something remarkable over the past 3 decades. Thanks to missions like Kepler, TESS, and the James Webb Space Telescope, we now know that planets aren't rare. They're everywhere. Current estimates suggest there could be as many as 100 billion planets just in our galaxy alone. Many of them, perhaps billions, orbit in what we call the habitable zone, that sweet spot where water can exist as a liquid, where life as we know it could potentially take root. So let's be conservative. Let's say only 0.1% of those habitable planets actually develop life, and of those, only 0.1% develop intelligent life. And of those, only 0.1% develop technology capable of communication or travel. You know what you still end up with? Thousands of potential civilizations, just in our galaxy, right now. This is what physicists call the Fermi paradox, named after Enrico Fermi, one of the architects of the atomic age. In 1950, during a casual lunch conversation at Los Alamos National Laboratory, Fermi posed a simple question that would echo through decades of scientific inquiry. Where is everybody? His reasoning was elegant and terrifying in its implications. The universe is 13.8 billion years old. Our sun? A mere 4.6 billion years old. That means there are stars out there with a head start of billions of years. Billions. If even one civilization emerged just 1 million years before us, they would have had enough time to colonize the entire galaxy, multiple times over. Yet we see nothing. We hear nothing. The cosmic silence is deafening. In 1961, astronomer Frank Drake attempted to quantify this mystery with an equation. When Drake first calculated this in the early 1960s, he estimated we might share the galaxy with thousands, possibly millions of technological civilizations. Modern calculations, using data from Kepler and other telescopes, often arrive at similar conclusions. And yet, here we are. Alone. So what's going on? Why haven't we been visited? Why haven't we detected their signals? Why does the universe seem so empty when mathematics screams it should be teeming with life? Some scientists propose what they call the Great Filter, the idea that somewhere in the chain of evolution from non-life to spacefaring civilization, there's a barrier. A filter so difficult to pass that almost no one makes it through. The terrifying question is that filter behind us or ahead of us? But today, we're exploring a different answer, one rooted not in biology or sociology, but in the cold, hard physics of the universe itself. Because here's what most people don't realize. The universe doesn't just make interstellar travel difficult, it makes it functionally impossible. And I'm not talking about technology. I'm not talking about resources or political will or any of those human concerns. I'm talking about the fundamental laws of physics, the same laws that govern every atom in your body, the same laws that dictate how stars burn and galaxies spin. These laws build walls, walls made of distance, walls made of time. walls made of energy requirements so astronomical they defy comprehension. Let me show you exactly what I mean. First, let's talk about distance. And I mean really understand distance. Because the numbers get so large so quickly that our brains simply can't process them intuitively. We need to feel them. The nearest star to Earth, Proxima Centauri, sits roughly 4.24 light-years away. A light-year is the distance light travels in 1 year. And light? Light moves fast. Really fast. 299,792 kilometers per second. That's fast enough to circle the Earth 7.5 times in a single second. At that speed, light from the Sun takes about 8 minutes to reach Earth. Light from Proxima Centauri takes 4.24 years. Now here's where it gets wild. The fastest human-made object ever created is the Parker Solar Probe, launched in 2018 by NASA. This incredible piece of engineering has reached speeds of approximately 192,000 kilometers per hour as it dives through the Sun's corona. At that speed, it's moving at about 0.06% the speed of light. Sounds impressive, right? It should. It's an engineering marvel. But here's the gut punch. At that speed, it would take the Parker Solar Probe roughly 6,900 years to reach Proxima Centauri. 6,900 years. To put that in perspective, 6,900 years ago, humans were just beginning to develop writing. The pyramids of Giza wouldn't be built for another 3,000 years. The entire span of recorded human history is shorter than the one-way trip to our nearest neighboring star. And Proxima Centauri, it's our closest neighbor. The stars beyond? They're incomprehensibly farther. Alpha Centauri A and B, part of the same triple-star system, are slightly farther. Barnard's star sits 6 light-years away. Sirius, the brightest star in our night sky, is 8.6 light-years distant. The Milky Way galaxy stretches roughly 100,000 light-years from edge to edge. 100,000. Even traveling at the speed of light itself, which, as we'll discuss, is impossible for any object with mass, it would take you 100,000 years to cross our galaxy. By the time you reach the other side, all of human civilization as we know it would be ancient history. Languages would have risen and fallen. Empires would have turned to dust. But let's say, hypothetically, that some alien civilization figured out how to travel at 10% the speed of light. That would be an absolutely staggering achievement. 10% of light speed is roughly 108 million kilometers per hour. At that velocity, you could travel from Earth to Mars in mere minutes. You could reach Neptune in under 5 hours. But Proxima Centauri? Still 42 years away. And that's our closest neighbor. This is the first wall. The wall of distance. Space is so vast, so incomprehensibly empty, that even traveling at velocities that would vaporize any known material, the journey times remain measured in decades, centuries, millennia. But distance is just the beginning. Because even if you could somehow overcome the time problem, even if you had generation ships or suspended animation or some other science fiction solution, you run headfirst into the second wall, the wall of physics itself. Einstein's theory of special relativity, published in 1905, fundamentally changed our understanding of motion, time, and space. And buried in those elegant equations is a cosmic speed limit, a law so fundamental that it appears to be woven into the fabric of reality itself. Nothing with mass can reach the speed of light. Not almost reach it. Not get really close. Cannot reach it. Period. Here's why, and this is crucial to understand. As an object accelerates, as it gains speed, it also gains mass, not in the sense that more atoms appear, but in the sense that its relativistic mass, the mass that matters for physics calculations, increases. The faster you go, the heavier you become. This relationship isn't linear, it's exponential. As you approach the speed of light, your mass approaches infinity, and to accelerate infinite mass requires infinite energy. Infinite energy doesn't exist. Therefore, you can't reach the speed of light if you have any mass at all. Only massless particles, photons of light and gluons, and gravitational waves can travel at light speed. Because they have no rest mass, they don't face this barrier. But anything made of matter, anything composed of atoms, anything with mass, cannot reach that ultimate velocity. Now, you might be thinking, okay, fine, we can't reach light speed. But what about 99% of light speed? 95%? Surely that's achievable with enough technology, right? Let me give you some numbers that'll make your head spin. According to recent calculations published in 2025, just to accelerate a tiny 2-gram spacecraft to 20%, the speed of light would require approximately 10 terawatt-hours of energy. 10 terawatt-hours. That's roughly the total energy consumption of a city of 1 million people for an entire year, for a spacecraft weighing less than a nickel. Now scale that up. Imagine you want to send something useful. Not a 2-gram chip, but an actual spacecraft with instruments, computers, communication equipment, radiation shielding. Let's say 1 ton. That's 1,000 kilograms. 500,000 times more massive than our 2-gram probe. The energy required doesn't scale linearly. It scales proportionally with mass. You're now looking at energy requirements equivalent to multiple nuclear power plants running for decades for a single spacecraft to reach just 20% of light speed. And remember, 20% of light speed still means a 21-year journey to Proxima Centauri, each way. But the energy problem gets worse, much worse, because we haven't even talked about fuel. See, there's a fundamental equation in rocketry called the Tsiolkovsky rocket equation, named after Russian scientist Konstantin Tsiolkovsky, who formulated it in 1897. This equation describes a harsh reality. To go faster, you need more fuel, but more fuel means more mass, and more mass means you need even more fuel to accelerate that fuel. It's a vicious cycle. Current chemical rockets, the kind we use to launch satellites and send probes to Mars, have what's called an exhaust velocity. That's how fast the rocket expels its propellant. For the best chemical rockets we have, hydrogen-oxygen engines like those used on the space shuttle, the exhaust velocity tops out around 4,500 meters per second. To reach even 1% of the speed of light, roughly 3 million meters per second, using chemical rockets, the amount of fuel you'd need is astronomical. Literally. We're talking about fuel masses millions or billions of times the mass of your payload. Let me put this in concrete terms. If you wanted to send a 1-ton spacecraft to Proxima Centauri using the best chemical rockets we have, arriving in, say, 400 years, the initial fuel mass would need to be greater than the mass of Mount Everest. 1 spacecraft, 1 mountain of fuel. Obviously, that's not practical, so engineers have proposed more advanced propulsion systems, nuclear rockets, fusion drives, ion engines, antimatter propulsion. Each of these improves the exhaust velocity. Ion drives, which we've actually built and tested on missions like NASA's Dawn spacecraft, can achieve exhaust velocities of around 30,000 to 50,000 meters per second. Much better than chemical rockets, but still nowhere near what you'd need for interstellar travel. Fusion rockets, if we could build them, might reach exhaust velocities of up to 10% the speed of light. That's 30 million meters per second. Incredible. Revolutionary. But the technology to sustain controlled fusion reactions for years or decades doesn't exist yet, despite decades of research and billions of dollars invested. And antimatter? Antimatter propulsion could theoretically approach 50% the speed of light. When matter and antimatter annihilate each other, they convert mass directly into energy with 100% efficiency, according to Einstein's famous equation E equals mc squared. But here's the problem. We can barely produce antimatter at all. The total amount of antimatter produced at CERN, the world's largest particle physics laboratory over decades of operation, is measured in nanograms, billionths of a gram. To fuel an antimatter rocket for an interstellar journey, you'd need kilograms, tons perhaps. At current production rates and energy costs, creating enough antimatter for a single mission would require more energy than human civilization has produced in its entire history. So we hit another wall. The wall of energy, the wall of physics, the wall that says, even if you know where you want to go, even if you have the technology, the sheer energy requirements make the journey effectively impossible with any foreseeable technology. But wait, let's play devil's advocate. Let's imagine an alien civilization far more advanced than us. A civilization that's been around for 1 million years, They've solved fusion. They've figured out antimatter production. They've built spacecraft capable of reaching 10%, maybe 20% the speed of light. They point their ship at Earth and begin the journey. From Proxima Centauri, that's a 42-year trip at 10% light speed. Long, but manageable, right? Maybe they're long-lived. Maybe they use generation ships. Maybe they've solved aging. Here's where the universe throws up yet another wall, one that most people never consider. Space isn't empty. I know, that sounds contradictory. Space is called space precisely because it's mostly vacuum, right? But mostly is doing a lot of work in that sentence. Because even the vacuum of interstellar space contains matter. Hydrogen atoms, dust particles, cosmic rays, micrometeoroids. The density is incredibly low. In the local interstellar medium, the region of space between stars near our Sun, there's approximately 1 atom per cubic centimeter. For comparison, air at sea level on Earth contains about 10 to the 19th power. That's 10 million trillion atoms per cubic centimeter. So yeah, space is pretty empty. But when you're moving at 10% the speed of light, that 1 atom per cubic centimeter becomes a problem. A big problem. At those velocities, every particle you encounter hits your spacecraft with enormous kinetic energy. The energy of a collision scales with the square of velocity. Double your speed, quadruple the impact energy. At 10% light speed, a single hydrogen atom, the lightest element in the universe, hits with the energy of a bullet. A single grain of sand, a particle a millimeter across, impacts with the force of multiple tons of TNT exploding. Your spacecraft isn't flying through space. It's being sandblasted by nuclear-level impacts, constantly, for decades. The erosion would be catastrophic. Any exposed surface would be worn away. Electronics would be fried by radiation. The hull would need to be incredibly thick, incredibly robust, probably multiple meters of shielding, which adds mass, which requires more fuel, which brings us back to the energy problem. Some scientists have proposed using magnetic fields to deflect charged particles, essentially creating a magnetic shield like Earth's magnetosphere protects us from solar wind. But that requires enormous amounts of energy to maintain, and it doesn't help with neutral particles or dust grains. Others have suggested putting a sacrificial shield in front of the spacecraft, a thick chunk of ice or metal that absorbs the impacts. But again, mass, energy, the problems compound. And we haven't even mentioned cosmic rays. High-energy particles, mostly protons, that zip through space at near-light speeds. They penetrate everything. On Earth, we're protected by our atmosphere and magnetic field. In space, on a decades-long journey, the radiation exposure would be lethal to any biological organism we know of. You'd need heavy shielding, probably liquid hydrogen or water, meters thick. More mass, more energy. Speaking of which, you know what else we recently discovered? We found thousands of exoplanets, worlds orbiting other stars. And you know what we learned? You should check out my video on James Webb's discovery of Earth 3.0, where we dive deep into what these incredible new worlds tell us about the possibility of life beyond our solar system. It'll blow your mind how much we've learned in just the past few years. The link is right in the description and on the card above. So we have walls of distance, walls of energy, walls of physics that prevent acceleration to light speed, walls of interstellar debris that sandblast your ship into oblivion. Each one alone is daunting. Together, they seem insurmountable. But there's more. Because even if some hypothetical super-advanced alien civilization solved all of these problems, even if they built a spacecraft that could travel at a significant fraction of light speed, survive the journey, and arrive at Earth, they face one more problem: time. Not just the time it takes to travel, but time itself behaves strangely at high velocities. Einstein's special relativity tells us that time is not absolute, it's relative. It flows at different rates depending on your motion. The faster you move, the slower time passes for you relative to a stationary observer. This isn't science fiction, this is measured fact. We've confirmed it thousands of times with atomic clocks on airplanes, satellites, and particle accelerators. GPS satellites have to account for relativistic time dilation or they'd give you the wrong location within minutes. The effect is small at everyday speeds. If you spend your life flying on airplanes, you'll age perhaps a few microseconds less than if you'd stayed on the ground. Hardly noticeable. But at relativistic speeds, speeds approaching light speed, the effect becomes dramatic. At 90% the speed of light, time slows down by a factor of about 2.3. For every year that passes for you on the ship, 2.3 years pass for everyone else in the universe. At 99% light speed, the factor is about 7. At 99.9%, it's 22. At 99.99%, you're looking at time dilation factors of 70 or more. For the travelers, this might actually be a benefit. A journey to a star 10 light-years away, at 99.99% light speed, might feel like only a few months to those aboard. But back home, back on their planet, 10 years have passed. Maybe more, depending on acceleration and deceleration phases. Now think about what this means for a civilization attempting to explore or colonize the galaxy. You send out a ship. From your perspective, they disappear into the void. Decades pass. Centuries, maybe. Do they make it? Do they survive? You might never know. And for those aboard, when they arrive at their destination, everyone they knew is gone. Their entire civilization might have changed beyond recognition, or collapsed entirely. They're stepping into a future they can't predict, can't communicate with, can't prepare for. This creates what scientists call the temporal isolation problem. Each interstellar mission becomes effectively cut off from its home civilization, not just by distance, but by time itself. The mission becomes autonomous, isolated, alone. There's no turning back, no calling home for help, no real-time communication. Because communication faces the same barriers as travel. Radio waves, light, all electromagnetic radiation travels at the speed of light. No faster. Send a message to Proxima Centauri, it takes 4.24 years to arrive. If they respond immediately, their answer takes another 4.24 years to get back to you. That's an 8.5-year round-trip conversation. One exchange of messages. Ask a question, wait 8.5 years for an answer. Try to coordinate anything, plan anything, share discoveries. It's functionally impossible. Imagine Earth trying to maintain a presence, a colony, an outpost, at another star system. Every decision, every crisis, every emergency has to be handled locally, because by the time you could ask for advice and receive it, decades have passed. Whatever situation prompted your question has long since resolved itself, one way or another. This isn't just an inconvenience, it fundamentally changes what's possible. It means interstellar civilizations can't really be civilizations in any meaningful sense. They fragment. They become isolated pockets of intelligence scattered across the void, each one alone, each one facing the universe without backup, without support, without connection. And there's another aspect of time dilation that makes things even stranger. Recent research published in 2025 explores something called redshifted civilizations. The paper, authored by researchers at the Czech Academy of Sciences, points out something fascinating and disturbing. If a civilization wanted to explore the galaxy within their subjective lifetime, they could theoretically use extreme time dilation near massive objects like black holes, orbit close to the event horizon of a supermassive black hole, like Sagittarius A star at the center of our galaxy, and time slows dramatically relative to the rest of the universe. For you orbiting the black hole, mere years might pass, but for the galaxy, for the universe, thousands or millions of years tick by. You could, in theory, use this as a kind of time machine, wait out the vast distances of the galaxy while the universe ages around you. But here's the catch. When you're in that time-dilated frame, any signals you send out are red-shifted, stretched, distorted. From the perspective of anyone else in the galaxy, your signals appear to come from somewhere moving away at high speeds, their frequency shifted down, their energy reduced. You become effectively invisible, undetectable. Communicating with you becomes nearly impossible because of the extreme time differences. By the time your message reaches someone, by the time they respond, you've subjectively moved years into the future. It's a solution that creates new problems. You can travel the galaxy, but you sacrifice connection with anyone else doing the same thing. You drift through time as much as space, a ghost ship in the cosmic ocean. Now, let's zoom out even further, because we've been talking about travel between nearby stars. Proxima Centauri, Alpha Centauri, Barnard's star. These are our immediate neighbors, the closest of the close, but the galaxy is 100,000 light-years across. Most stars are not nearby. Most stars are thousands, tens of thousands, hundreds of thousands of light-years away. At 10% light speed, crossing the galaxy takes 1 million years. 1 million years. Think about that time frame. 1 million years ago, humans didn't exist. Homo erectus walked the earth. No language, no agriculture, no civilization. Everything you think of as human culture, human achievement, all of it has happened in a tiny fraction of that time. Even at 50% light speed, a velocity that's almost certainly impossible to achieve and sustain, you're looking at 200,000 years to cross the galaxy. Modern humans, Homo sapiens, have only existed for about 300,000 years. You're talking about a journey lasting nearly as long as our entire species has been around. This is the scale we're dealing with. This is the reality of interstellar travel. It's not just hard, it's not just expensive. It operates on timescales that dwarf civilizations, that outlast species, that make the rise and fall of empires look like the blink of an eye. So when we ask, why haven't aliens visited Earth, we have to grapple with these numbers, these timescales, these energy requirements, these physical barriers. Let's say there is an alien civilization out there, a curious, exploratory species not unlike us. They develop technology, they build telescopes, they look out at the galaxy and wonder, just like we do, if anyone else is out there. They detect Earth, maybe they see our atmosphere, notice the oxygen, the signatures of life, or maybe they pick up our radio signals, our television broadcasts that have been leaking into space since the 1930s. They know we're here. They want to visit, to meet us, to exchange knowledge. They face the same walls we've discussed. The distance to Earth from wherever they are is measured in light years, dozens, hundreds, thousands of light years. They need to build a ship capable of sustaining a crew, or preserving them somehow, for journeys lasting centuries or millennia. They need energy, vast amounts of it, more than their entire civilization might produce in years. They need propulsion technology we can barely imagine. They need to solve the debris problem, the radiation problem, the time dilation problem, the communication problem. Even if they're 1 million years more advanced than us, even if they're a Type 2 civilization on the Kardashev scale, meaning they can harness the entire energy output of their star, the problems don't disappear. They just become slightly more manageable. Slightly. A Type 2 civilization could potentially build massive spacecraft, generation ships the size of cities, O'Neill cylinders, rotating habitats that generate artificial gravity through spin. They could sustain populations for centuries maybe, but the energy requirements to accelerate something that massive to even a fraction of light speed are still staggering. And here's a question that doesn't get asked enough. Why would they bother? From their perspective, even if they detect Earth, even if they know we're here, the cost-benefit analysis is brutal. Spend the resources of an entire star system to send a mission that will take thousands of years, whose success is uncertain, whose crew will never return or report back in any meaningful time frame, all to visit one planet among billions. Meanwhile, their own star system likely contains dozens or hundreds of worlds and moons and asteroids they could colonize, terraform, exploit, right there, in their backyard. No decades-long journey, no relativistic risks, just normal spaceflight, the kind we do within our own solar system right now. Even Mars, our nearest planetary neighbor beyond Venus, takes months to reach with current technology. But at least it's reachable. At least you can go there and come back within your lifetime. At least you can communicate with home with a delay of minutes, not years. The incentive to stay local, to develop your own solar system rather than venture into the interstellar void, is overwhelming. And if that's true for any alien civilization, it explains a lot about the Fermi paradox. Maybe they're out there. Maybe there are thousands of civilizations in the galaxy, but each one is locked in its own solar system, bound by the same physical laws that bind us, looking out, wondering, detecting hints of others, but unable or unwilling to bridge the gap. It's like islands in an infinite ocean, each one teeming with life, with culture, with intelligence. But the ocean between them is so vast, so dangerous, so expensive to cross, that they remain isolated, not by choice, but by necessity, by the fundamental structure of space-time itself. And there's one more factor we haven't discussed yet, one that's perhaps the most sobering of all: stability, or rather, the lack of it. Here on Earth, we've had technological civilization for what, a century? Maybe two if you're generous. We've been sending radio signals into space for less than 100 years. We've had the ability to destroy ourselves with nuclear weapons for about 80 years. We don't know how long we'll last. We don't know if we'll make it another century, another 1,000 years, another million. Climate change, nuclear war, artificial intelligence, pandemics, asteroid impacts. The list of existential risks is long and growing. Now apply that to any alien civilization. They face the same risks. Different specifics maybe, but the same categories: environmental collapse, warfare, technology running amok, resource depletion, societal collapse. How many civilizations make it past these filters? How many survive long enough to become truly interstellar? We don't know, but the Drake equation includes that variable. Remember? L, the average lifespan of a communicating civilization. If L is short, if most civilizations only broadcast for a few hundred or a few thousand years before collapsing or destroying themselves, then even if intelligence is common, the chances of two civilizations existing at the same time, close enough to detect each other, drops dramatically. Think of it like fireflies in a vast, dark forest. Each one blinks on for just a moment, then goes dark. If the forest is large enough, if the moments are brief enough, you might never see two fireflies lit at the same time, even if thousands of them blink throughout the night. The universe is 13.8 billion years old, but a technological civilization might only last 10,000 years, 100,000 if they're lucky. That's 0.0007% of cosmic history. A blink, a flicker, a candle in the wind. Two civilizations could exist in the same galaxy, separated by only a few hundred light-years, but if one rises and falls before the other emerges, they might as well be in different universes. They'll never know about each other, never communicate, never meet. This is called the temporal coordination problem, and it's just as insurmountable as the distance problem or the energy problem. Because even if you solve the technology, even if you build the ships and generate the power, you can't control when you exist. You can't choose to be born at the same cosmic moment as another civilization. Now, let's talk about something that really keeps astrophysicists up at night: the expansion of the universe itself. In 1929, astronomer Edwin Hubble made a discovery that changed everything. He found that distant galaxies are moving away from us, not because they're physically traveling through space, but because space itself is expanding. The fabric of the universe is stretching, carrying galaxies along with it. And here's the kicker: the farther away a galaxy is, the faster it's receding. This relationship is described by Hubble's law. The recession velocity equals Hubble's constant times the distance. Currently, Hubble's constant is measured at approximately 70 kilometers per second per megaparsec. What does that mean in practical terms? For every 3.3 million light-years of distance, objects are receding from us at about 70 kilometers per second faster. So a galaxy 3.3 million light-years away is moving away at 70 kilometers per second. One that's 6.6 million light-years away is receding at 140 kilometers per second, and so on. At some distance, called the Hubble distance or cosmic event horizon, objects are receding faster than the speed of light. Not because they're moving through space faster than light, which is impossible, but because the space between us and them is expanding faster than light can cross it. That distance is currently about 14 billion light-years. Anything beyond that is causally disconnected from us. Light from those regions will never reach us. We will never see them, never detect them, never communicate with them. They exist, but they're beyond our cosmic horizon. Forever. And here's the truly unsettling part. The universe's expansion is accelerating. Dark energy, a mysterious force we don't fully understand, is pushing the expansion faster and faster. Galaxies that are currently within our observable universe will eventually cross that horizon and disappear from view. In the far future, in trillions of years, observers in our galaxy will look out and see nothing, just empty space. All other galaxies will have receded beyond the cosmic horizon. But that's the deep future. What about now? What about civilizations in our galaxy, in our local group of galaxies? Well, our galaxy, the Milky Way, and our nearest large neighbor, Andromeda, are actually moving toward each other. They're gravitationally bound, part of what's called the local group, which includes about 54 galaxies. Within this group, gravity overcomes the expansion of space. We're stuck together cosmically speaking. Andromeda is about 2.5 million light-years away. It's moving toward us at about 110 kilometers per second. In about 4.5 billion years, the Milky Way and Andromeda will collide and merge into a single, giant elliptical galaxy. So within our local group, the expansion of the universe doesn't prevent travel or communication, but it's still 2.5 million light-years to Andromeda. At 10% light speed, that's a 25 million year journey. 25 million years. Longer than humans have existed as a genus. Longer than most species survive. Beyond the local group, though, galaxies are receding. The Virgo cluster, a collection of about 1,500 galaxies, sits about 65 million light-years away, and it's moving away from us at about 1,000 kilometers per second due to the expansion of space. To reach a galaxy in the Virgo cluster, you'd need to account for that recession. You're not just crossing 650 million light-years at 10% light speed, which would take 650 million years. You're chasing a target that's actively moving away from you. Depending on the expansion rate and acceleration, some targets might be functionally unreachable even if you traveled at light speed itself. The universe is not just vast, it's growing. The gaps are widening. Every second, space expands by about 70 kilometers for every 3.3 million light-years of distance. It's subtle on small scales, but over cosmic distances, it's insurmountable. So when we talk about aliens visiting Earth, we have to ask, where are they coming from? If they're in our galaxy, they face all the problems we've discussed: distance, energy, time, debris, radiation. If they're from another galaxy, they face those same problems multiplied by factors of thousands or millions, plus the expansion of space itself working against them. The odds, already slim, become vanishingly small. Let's do some actual math here. Let's calculate what it would take for an alien civilization to visit Earth from Proxima Centauri, our closest stellar neighbor, at 4.24 light-years. Assume they've built a spacecraft with a mass of 1,000 tons. That's small by spaceship standards, but let's be generous. They want to reach 10% the speed of light to make the journey in about 42 years. Using the relativistic rocket equation, accounting for the fuel needed to accelerate the ship and the fuel itself, you run into a problem immediately. If you're using chemical rockets, it's impossible. Literally impossible. The fuel required exceeds the mass of the observable universe. Okay, fine. Use nuclear fusion. Assume they've perfected fusion drives with an exhaust velocity of 10% light speed. Now the math becomes merely ridiculous instead of impossible. The fuel mass would need to be approximately equal to the ship's mass. So, 1,000 tons of fuel for a 1,000-ton ship. But wait, you also need to slow down when you arrive at Earth. Otherwise, you zip past at 10% light speed and the encounter lasts a fraction of a second. Useless for any meaningful contact. So you need fuel to decelerate. Now you're looking at fuel masses significantly larger than the ship itself. Maybe 10,000 tons? Maybe more, depending on efficiency and engineering details. And remember, this is just to reach 10% light speed. To go faster, the fuel requirements increase exponentially. Where does that fuel come from? How do you gather it? Hydrogen is abundant, sure, especially in gas giants, but you need to mine it, refine it, contain it, Fusion fuel deuterium and tritium are much rarer. Deuterium makes up about 0.015% of natural hydrogen. Tritium is even rarer, radioactive with a half-life of 12.3 years. You'd likely need to breed it artificially using lithium. The infrastructure required is staggering. Fleets of mining ships, processing facilities, storage tanks, launch facilities. You're talking about an industrial effort that dwarfs anything humanity has ever attempted. And that's just for one ship, one mission. Now multiply that by however many missions you'd want to send out. To explore even just the nearby stars, the few dozen within 10 or 20 light years, you'd need dozens of ships, each one requiring thousands of tons of fuel, each one representing decades or centuries of industrial output. And for what? To reach worlds that might be dead rocks, or ocean worlds with no land, or gas giants with crushing gravity and no surface. The chances that you'd find something worthwhile, something that justifies the expenditure, are small. Not zero, but small. This is the economic wall. Even if you can do something technically, even if the physics allows it, you run into resource constraints, opportunity costs, risk versus reward calculations. An advanced civilization has to ask itself, is it worth spending the equivalent of our entire industrial output for a decade to send a single ship to a single nearby star, knowing it won't return, knowing we won't hear back for decades or centuries, knowing the odds of finding anything useful are low? Or should we invest those resources closer to home, building habitats, developing our own worlds, conducting science and exploration within our solar system, where communication is measured in minutes or hours, not years, where missions can be monitored, adjusted, supported? The answer seems obvious, and if it's obvious to us, it's probably obvious to any alien civilization as well. This might be the real answer to the Fermi paradox. Not that intelligence is rare, not that life is rare, but that interstellar travel is simply not worth doing. The costs are too high, the timescales too long, the risks too great, the rewards too uncertain. Every civilization reaches the same conclusion. Stay home, develop locally. Listen, sure, send signals maybe, hope someone out there hears and responds, but don't attempt the journey. Don't send ships into the void. It's a waste of resources that could be better used ensuring your own survival and prosperity. There's a concept in evolutionary biology and game theory called the dark forest hypothesis. It's taken from a science fiction novel by Chinese author Liu Cixin, but the underlying logic is disturbingly sound. The idea goes like this: the universe is like a dark forest. Every civilization is a hunter creeping through the trees. They know other hunters exist. But revealing your position is dangerous, because you don't know if the other hunter is friendly or hostile. You don't know their capabilities, their intentions, their morality. The safest strategy, the one that maximizes your survival, is to stay quiet, stay hidden. And if you do detect another civilization, if you stumble across another hunter in the dark, you face a terrible calculation. Do you reveal yourself? Risk potential friendship, but also risk potential destruction? Or do you stay silent? Or, most chillingly, do you eliminate the threat before it can eliminate you? This hypothesis suggests that advanced civilizations might deliberately avoid contact, not because travel is impossible, but because it's dangerous. Revealing yourself, sending out signals, announcing your presence to the cosmos is like shouting in that dark forest. You don't know who's listening. You don't know what they'll do with that information. Now, I don't personally find this hypothesis compelling as a complete explanation for the Fermi paradox. It requires all civilizations to be paranoid and hostile, which seems like a pessimistic assumption. But it does highlight something important. Even if travel is possible, even if you could reach other stars, you might choose not to. Fear, caution, self-preservation. These are powerful motivators, and they might keep civilizations locked in their home systems just as effectively as physics does. But let's get back to the physics, because there's another aspect we need to discuss: navigation. Space is big. We've established that. But it's not static. Everything is moving. Earth orbits the Sun at about 30 kilometers per second. The Sun orbits the center of the Milky Way at about 220 kilometers per second. The Milky Way itself is moving through the local group, and the local group is moving through the universe. When you aim for a star system, you're not aiming for where it is now. You're aiming for where it will be when you arrive, which, at interstellar distances and travel times measured in decades or centuries, is very different. Proxima Centauri is moving relative to the Sun at about 22 kilometers per second. Over 42 years, the duration of a 10% light speed journey, it will have moved about 29 billion kilometers. That's approximately the distance from the Sun to Neptune. You need to account for that in your trajectory, and you need to do it with incredible precision. Because if your calculations are off by even a fraction of a degree, at interstellar distances you'll miss your target by light years. You'll sail past into the void with no way to correct course, no way to turn around, no way to recover. Remember, at 10% light speed, you're moving so fast that conventional rocket burns barely affect your trajectory. Turning requires enormous amounts of fuel and time. You can't just point and shoot. You need to calculate everything in advance, account for the motion of your target, the motion of your starting point, gravitational influences from other stars and planets along the way. It's like trying to hit a moving target from a moving platform with a bullet that takes 42 years to arrive. The precision required is mind-boggling. And we haven't even talked about detection. How do you know where you're going? How do you see obstacles in your path? At 10% light speed, you're covering about 30 million kilometers every 1,000 seconds. That's 300 kilometers per second. Anything in your path, any asteroid or comet or rogue planet, you'll hit before you have time to react. Light speed is the ultimate speed limit, including for information. You can't detect something and avoid it faster than light can travel from that object to your sensors. At relativistic speeds, your reaction time is compressed. You're racing your own detection capabilities. Some proposals involve sending a small probe ahead, something that scouts the route and reports back on hazards. But at these speeds, by the time the probe detects something and the signal reaches your ship, you might have already collided. The coordination required is incredibly complex. This is yet another wall, the navigation and detection wall. Space is vast and mostly empty, but mostly isn't good enough when you're moving at a significant fraction of light speed. Even a small error, even a tiny piece of debris can be catastrophic. Now let's talk about what happens if, despite all these obstacles, an alien ship somehow makes it to Earth. They've overcome the distance, the energy requirements, the debris, the radiation, the navigation challenges. They're here. They arrive in our solar system. What do they find? Well, first, they find a system full of traffic. Human traffic. We've launched thousands of satellites. The International Space Station orbits at about 400 kilometers altitude. Geostationary satellites sit at 35,000 kilometers. We've sent probes to every planet. We've scattered debris throughout near-Earth space. An incoming ship traveling at even a fraction of light speed can't just slam on the brakes. Deceleration takes time and distance. Lots of both. They'd need to start slowing down well before entering the solar system, probably while still in the outer reaches, beyond Neptune's orbit. The deceleration phase requires just as much energy as the acceleration phase, maybe more, because you can't use gravity assists or solar sails effectively when you're trying to slow down. You need fuel, reaction mass, energy. If they somehow manage to decelerate into a stable orbit, now what? Do they announce themselves? Do they try to communicate? How do they approach without being seen as a threat? Imagine the reverse. Imagine humanity finally builds an interstellar ship. We send it to Proxima Centauri. It arrives after 42 years. What does it find? Maybe nothing. Maybe Proxima Centauri b, the planet we've detected orbiting in the habitable zone, is sterile, a dead world. All that effort, all that energy, all those decades, for nothing. Or maybe there's life, microbial life, perhaps. Interesting scientifically, but hardly worth the cost of the mission. We could have studied microbial life on Europa or Enceladus, moons in our own solar system, for a fraction of the cost and time. Or maybe, just maybe, there's intelligent life, a civilization. Now what? Do they welcome us? Are they even similar enough to us that communication is possible? Do they see us as threats, as opportunities, as curiosities? The unknowns are staggering. The risks are immense, and there's no way to know until you arrive, and by then you're committed. You can't turn around. You can't go home. You're there for better or worse. This is the commitment problem. Interstellar travel isn't just expensive and dangerous, it's irreversible. Every mission is a one-way trip. Effectively, even if you could theoretically return, the time involved means everyone you knew is gone. Your civilization has changed. You're returning to a future, not a home. That level of commitment, that degree of uncertainty, makes interstellar travel not just a technological challenge, but a psychological and sociological one. What kind of individuals would undertake such a journey? What kind of society would send them? And here's something most people don't consider. Let's say you're an alien civilization. You've detected Earth. You know there's oxygen in the atmosphere, a signature of life. Maybe you've even detected techno-signatures, radio signals, signs of industrial activity. You know Earth is inhabited. You know we're here. But from your perspective, decades or centuries away, you have no idea what our capabilities are. Are we peaceful, warlike, advanced, primitive? By the time you arrive, we could have changed completely. Remember, if you're 400 light-years away and you detect our radio signals from the 1930s, you're seeing us as we were in the 1930s. You're seeing a civilization with propeller planes and early computers. You have no idea we now have nuclear weapons, satellites, space stations, global communication networks. By the time you travel those 400 light-years, arriving in the year 2430, assuming you left immediately upon detecting us, Earth will have changed in ways neither you nor we can predict. You're arriving blind, 400 years out of date, hoping we're still there and still willing to meet you. The information lag is just as problematic as the travel time. You're always working with outdated intelligence, always guessing, always uncertain. Let's take a step back and think about this from a purely mathematical perspective. The Drake equation, which we discussed earlier, attempts to estimate how many communicating civilizations exist in our galaxy right now, but there's a modified version that's perhaps more relevant to our question about visitation. Some researchers have proposed what they call the contact equation, or the visitation probability. It takes the Drake equation and adds factors for the ability and willingness to engage in interstellar travel. The equation looks something like this. The probability of contact equals the number of civilizations times the fraction that develop interstellar travel capability times the fraction of the galaxy they can reach times the overlap time between civilizations. Let's be wildly optimistic. Let's say there are 10,000 civilizations in the Milky Way right now. That's much higher than most estimates, but let's roll with it. Now, what fraction of those develop interstellar travel capability? Based on everything we've discussed, the energy requirements, the timescales, the risks, let's generously say 10%. 1,000 civilizations out of 10,000 manage to build ships capable of crossing interstellar space. Now, what fraction of the galaxy can each civilization reach? The Milky Way is 100,000 light-years across. Even traveling at 10% light speed, crossing it takes 1 million years. Most civilizations probably don't last that long. So let's say each spacefaring civilization can reach, on average, 1% of the galaxy. Maybe they send ships to nearby stars, establish a few colonies or outposts within a few hundred light-years. 1,000 civilizations, each reaching 1% of the galaxy. But the galaxy is huge. The probability that their 1% overlaps with our location is small. Let's say only 10 of those 1,000 civilizations are within range of Earth. Now, of those 10, how many actually choose to visit Earth specifically? They might have detected hundreds or thousands of potentially interesting targets, planets with life signatures, unusual stellar phenomena, resource-rich systems. Earth is just one option among many. Maybe one or two choose to come here. And finally, the overlap time. How long have we been detectable? Radio signals leak into space starting in the 1930s. So call it 95 years as of 2026. Those signals have reached stars within 95 light-years. That's a sphere of space containing about 14,000 stars. Sounds like a lot. but the Milky Way contains 200 billion to 400 billion stars. 14,000 is 0.007% of the galaxy. So any civilization more than 95 light-years away hasn't even detected us yet. They don't know we're here. They have no reason to visit. For civilizations within that 95 light-year sphere, they detected our earliest signals recently. If they immediately launched a ship traveling at 10% light speed, they're still decades or centuries away from arriving, and we're assuming they detected us, which isn't guaranteed. Our radio signals aren't that strong. They fade with distance, drowned out by cosmic noise. The Arecibo message, a powerful directed signal sent toward the globular cluster Messier 13 in 1974, would be barely detectable even with our best radio telescopes if someone sent it to us from a similar distance. So the probability of contact, of visitation, when you actually run through the numbers, is incredibly small. Not zero, but small enough that we shouldn't be surprised we haven't been visited. The absence of alien spacecraft in our skies isn't a mystery. It's the expected result given the constraints of physics and probability. But there's one more angle to consider, one that requires us to think even bigger. Beyond our galaxy, beyond the local group. What about civilizations in other galaxies? Could they reach us? The nearest large galaxy is Andromeda, 2.5 million light-years away. At 10% light speed, that's a 25 million-year journey. Longer than primates have existed on Earth, longer than most mammalian species survive before going extinct or evolving into something else. No individual, no matter how long-lived, makes that journey. No generation ship could sustain a population for that long without either collapsing or evolving into something unrecognizable. The ship itself would degrade, systems would fail, entropy would win. Maybe an artificial intelligence could do it. A robotic probe with no biological passengers, no need for life support, just instruments and computers designed to last millions of years. But even that faces challenges. Cosmic rays gradually damage electronics. Moving parts wear out. Information storage degrades. And for what purpose? To visit one galaxy among trillions. Even if Andromeda is teeming with civilizations, why would any of them expend the resources to send a probe to the Milky Way? What could they possibly learn that justifies a 25 million-year mission? The scales are just too vast, the timelines too long, the payoff too uncertain. And remember, Andromeda is our nearest large neighbor. Most galaxies are much farther, hundreds of millions of light-years, billions of light-years. At those distances, even light itself, traveling at the cosmic speed limit, takes eons to cross the gap. By the time light from those distant galaxies reaches us, we're seeing them as they were billions of years ago. The civilizations that might have existed then could be long extinct, or evolved beyond recognition, or ascended to some incomprehensible form we couldn't even detect. This is the cosmic horizon problem. Not just the literal event horizon created by the expansion of space, but the practical horizon created by time itself. The universe is so old, so vast, that simultaneity becomes meaningless. When we talk about now on a cosmic scale, we're really talking about different eras separated by millions or billions of years. An alien civilization in a galaxy a billion light-years away, in their now, might be looking at Earth as it was a billion years ago, when life was still single-celled organisms floating in ancient oceans. They have no idea humans exist, no idea Earth is worth visiting, and we, looking at their galaxy, see it as it was a billion years ago. We have no idea if they exist now. Maybe they arose and flourished and died in the billion years it took their light to reach us. We're seeing ghosts, echoes of a past that might not connect to the present in any meaningful way. This is perhaps the most profound barrier of all. Not physics, not energy, not distance, but time itself. The universe is not just a place. It's a story unfolding over billions of years, and different parts of the story are happening at different times, separated by distances so vast that cause and effect break down. You can't have a conversation with someone a billion light-years away. By the time your message reaches them, a billion years have passed. By the time their response reaches you, another billion years. That's not communication. That's archaeology. You're studying the past, not interacting with the present. Now, Some of you might be thinking, what about wormholes? What about warp drives? What about technologies that bend or break the rules? These are staples of science fiction, and for good reason. They're imaginative, exciting, and they solve the interstellar travel problem neatly. But here's the uncomfortable truth. We have no evidence these things are possible. None. Wormholes are solutions to Einstein's equations of general relativity. They're mathematically valid, but creating one, stabilizing one, making it traversable, requires exotic matter with negative energy density. We've never observed such matter. We don't know if it exists. Most physicists suspect it doesn't, or if it does, it exists only in quantum foam at the Planck scale, far too small to be useful. Warp drives, like the Alcubierre drive proposed in 1994, also require exotic matter. They work by contracting space in front of the ship and expanding it behind, effectively moving the ship faster than light without actually accelerating it through space. Clever. But again, exotic matter, negative energy. Things we don't have and don't know how to get. And even if you could build a warp drive, recent calculations show it would require the mass-energy equivalent of Jupiter, the entire planet, converted to energy, for one ship. Kugelblitz drives, microscopic black holes used as engines, face similar problems. Creating a black hole requires compressing enormous amounts of energy into a tiny space. The energy requirements are absurd. And even if you managed it, the black hole would evaporate via Hawking radiation on timescales measured in seconds or less, unless you kept feeding it mass energy constantly. Every proposed faster-than-light or near-light-speed technology runs into the same walls. Energy, exotic matter, unproven physics. They're theoretically interesting but practically impossible with anything resembling known physics. Could there be new physics? Undiscovered principles that allow faster-than-light travel or circumvent the energy requirements? Maybe. We don't know everything. Our understanding of the universe is incomplete. But here's the thing. We know a lot. General relativity has been tested to extraordinary precision. Special relativity is confirmed every day in particle accelerators. The laws of thermodynamics haven't been violated in any experiment ever conducted. These aren't hunches or guesses. They're robust, well-tested theories that describe reality with incredible accuracy. To overturn them or even to find loopholes, you need evidence, observations, experiments. And so far, despite a century of looking, we haven't found any. Could an alien civilization have discovered something we haven't? Could they know physics we don't? It's possible, but unlikely for a specific reason. Physics isn't arbitrary. It's not something you can just invent or wish into existence. The laws of physics are constraints imposed by the universe itself. They're discovered, not created, and they appear to be universal. The spectral lines of hydrogen observed in a galaxy 10 billion light-years away are identical to the spectral lines of hydrogen in a laboratory on Earth. The speed of light is the same everywhere we've measured it. Gravity behaves the same way around distant stars as it does around our sun. The universe operates on consistent principles. If faster-than-light travel were possible, we'd expect to see evidence of it somewhere. Natural phenomena that exceed light speed, particles that violate causality. Something. We don't. Every observation, every measurement, every experiment confirms that light speed is the limit for information and matter. It's not just a good idea. It's the law. An advanced civilization might have better technology than us, better engineering, more sophisticated computers, but they're still bound by the same physical laws. They can't violate thermodynamics any more than they can decide gravity shouldn't apply to them. This is a humbling realization. We like to think that with enough advancement, enough time, anything becomes possible. But the universe doesn't care what we think is fair or reasonable. It operates on principles that constrain everyone equally, regardless of intelligence or technological sophistication. Now, there is one scenario that occasionally gets proposed that's worth considering. What if aliens don't send biological beings? What if they send machines? Artificial intelligence, self-replicating probes that could explore the galaxy over millions of years. This is called the von Neumann probe concept, named after mathematician John von Neumann, who theorized about self-replicating machines. The idea is elegant. You build a probe capable of traveling to another star system, mining resources there, building copies of itself, and sending those copies to yet more star systems. Each probe makes 2 copies. Those 2 make 2 each. 4 becomes 8, 8 becomes 16, and so on. Exponential growth. With this strategy, even traveling at a modest fraction of light speed, you could explore every star system in the galaxy within a few million years. It's a clever solution to the time problem. No single probe needs to visit more than a few star systems. The collective fleet growing exponentially covers everything. But this introduces new problems. First, self-replication is incredibly complex. You need mining equipment, refining facilities, manufacturing capabilities, quality control, all miniaturized and automated to the point where a machine can build a perfect copy of itself from raw materials. We can't do this yet. Not even close. Our most advanced robots require massive industrial infrastructure, human oversight, carefully refined materials. Building something that can land on an asteroid, extract ore, process it, manufacture components, and assemble a working copy of itself is science fiction territory. Maybe an advanced civilization could do it, but it's not trivial. And there's another problem: control. Self-replicating machines have a disturbing tendency to mutate. Errors creep in. A tiny flaw in the replication process, and subsequent generations inherit and amplify that flaw. Over thousands or millions of generations, spanning light years and millennia, these probes could evolve, drift from their original programming, become something their creators never intended. This is actually a potential answer to the Fermi paradox. Maybe alien civilizations don't send von Neumann probes because they're terrified of creating a runaway replication scenario. A gray goo situation where self-replicating machines spread uncontrollably, consuming resources, filling the galaxy with mutated descendants that no longer serve any useful purpose. The risk versus reward calculation doesn't favor it. You could explore the galaxy, sure, but you might also unleash something you can't control. Something that could even threaten your home system when mutated probes eventually return. So even the clever solutions have problems. Even the workarounds introduce new risks and challenges that might explain why nobody does them. Let's pivot and talk about detection, because even if physical travel is impossible or impractical, what about communication? What about radio signals, laser transmissions, some form of deliberate messaging between stars? This is what SETI, the Search for Extraterrestrial Intelligence, has been doing since 1960. They scan the skies with radio telescopes, listening for signals that don't match natural phenomena, patterns, repetitions, narrowband transmissions, anything that screams artificial. And in over 60 years of searching across millions of star systems, they've found nothing. Well, nothing confirmed. There was the WOW signal in 1977, a strong narrowband radio signal detected by the Big Ear telescope that lasted 72 seconds and never repeated. But we don't know what it was. Could have been terrestrial interference, could have been a natural phenomenon we don't understand. Without repetition, we can't say. Why the silence? If civilizations can't travel, why aren't they at least broadcasting? Several reasons. First, maybe they are, and we're not listening the right way. We've searched a tiny fraction of the sky, at a limited range of frequencies, for a limited amount of time. The universe is vast. Our searches have been like dipping a cup into the ocean and concluding there are no fish because we didn't catch any. Second, maybe advanced civilizations don't use radio. We've only been using radio ourselves for about a century. Already we're transitioning to more efficient technologies. Fiber optics, tight beam communications, digital transmissions that leak less energy into space. An advanced civilization might communicate in ways we can't detect. Neutrino beams, gravitational waves, quantum entanglement, or methods we haven't even imagined yet because we don't know the physics. Third, maybe they're deliberately quiet. The dark forest hypothesis again. Broadcasting your location to unknown listeners is a risk. Maybe most civilizations listen but don't transmit. Everyone's waiting for someone else to go first. Fourth, maybe the window of detectability is short. A civilization might broadcast loudly for a few hundred years, then transition to quieter technologies. If that's the norm, and if civilizations are rare, the chances of two civilizations broadcasting at the same time, within detection range of each other, drops dramatically. Imagine Earth's radio bubble. It's been expanding since the 1930s, 95 light-years in radius. Within that bubble, we're detectable, at least in principle. But our signals are getting weaker as we transition to digital, to satellites, to fiber optics. In another century, we might be nearly radio silent from an external perspective. If every civilization has a similar arc, a brief loud period followed by quiet, then the galaxy could be full of civilizations that simply aren't broadcasting when and where we're listening. And fifth, maybe intelligence is just incredibly rare. Maybe Earth is one of the very few planets where evolution stumbled onto complex nervous systems, symbolic thought, tool use, language, cumulative culture. Maybe the filter isn't technology or survival, but intelligence itself. Life might be common. Microbial mats, simple multicellular organisms, even complex ecosystems. But intelligence? That might be a 1 in a trillion fluke, an evolutionary accident that almost never happens. If that's true, we might be alone in the galaxy, or at least so rare that the distances between intelligent civilizations are measured in millions of light-years rather than hundreds or thousands. The silence doesn't prove anything. It's consistent with many explanations, but combined with the impossibility of travel, it paints a picture of a universe that's vast, ancient, possibly teeming with life, but ultimately isolating. Each island of intelligence emerges, looks out at the stars, wonders if anyone else is there, and finds no answer, because the answers, if they exist, are too far away to reach or too quiet to hear. Now, I want to address a common objection. People often say, "But you're assuming alien technology is limited like ours. What if they're a million years more advanced? What if they can do things we can't even imagine?" It's a fair point, and it's true that our imagination is limited by our experience. Medieval peasants couldn't have imagined the internet. Ancient Greeks couldn't have predicted nuclear power. So yes, there are almost certainly technologies we haven't conceived of yet. But here's the distinction. Technology exploits the laws of physics. It doesn't override them. The internet is impressive, but it doesn't violate causality. Nuclear power is powerful, but it doesn't break conservation of energy. Advanced technology is better at working within the rules. More efficient, more clever, but it's still working within the rules. And some of those rules are fundamental. Energy requirements are fundamental. You can't accelerate a massive object to high speeds without putting energy into it. You can be more efficient about it, waste less energy as heat or radiation, but you can't eliminate the requirement. The speed of light is fundamental. It's not a technological limit. It's a structural property of space-time. Moving faster than light doesn't just require better engines. It requires space-time to behave differently than all our observations suggest it does. Time dilation is fundamental. Traveling at high speeds means time passes more slowly for you relative to the rest of the universe. That's not a bug to be fixed. It's how time works. So yes, a million-year-old civilization might have technology that looks like magic to us, but it's still bound by conservation of energy, by thermodynamics, by relativity. These aren't suggestions. They're the structure of reality itself. Think of it like this. Imagine explaining to someone from ancient Rome that we have machines that let us fly through the air at hundreds of kilometers per hour. They'd think you were describing magic, divine power, something beyond the laws of nature. But we're not. Airplanes work because of aerodynamics, combustion, materials science, all of it operating within the laws of physics that existed in ancient Rome just as they exist today. The Romans didn't know those laws, but the laws were still there, constraining what was possible. Our technology seems miraculous to them, but to us it's just clever application of natural principles. We haven't violated any fundamental laws. We've just learned to exploit them better. The same logic applies to alien civilizations. They might know more physics than we do. They might have discovered principles we haven't. But those principles still have to be consistent with everything else we've observed. They can't contradict relativity, which has been tested to 1 part in 10 to the 15th power. They can't violate thermodynamics, which has never been broken in any experiment ever. So when we calculate the energy needed to accelerate to relativistic speeds, when we point out the time dilation effects, when we discuss the cosmic speed limit, we're not being parochial or limited. We're describing constraints that appear to be universal, fundamental, and inescapable. Could we be wrong? Could there be loopholes we haven't found? Sure. Science is always provisional, always open to revision with new evidence, but the burden of proof is on the claim that these fundamental laws can be circumvented, and so far we have no evidence that they can be. Now let's talk about something that often gets overlooked in these discussions: motivation. We've focused a lot on the physical impossibility or impracticality of interstellar travel, but even if it were possible, even if you could build ships and generate the energy and survive the journey, would you want to? Human history is full of exploration. Polynesians crossing the Pacific in outrigger canoes, Vikings sailing to North America, European explorers circumnavigating the globe. We're a curious species. We go places because they're there. But notice something about all those examples. The journeys were hard, sure. Dangerous, absolutely. But they were survivable. Weeks or months, occasionally a year or two. Not decades, not centuries, not millennia. And there was always a reasonable expectation of discovery. New lands, new resources, trade routes, places where people could live, settle, thrive. Interstellar travel offers none of that. The journey doesn't last months. It lasts longer than civilizations. And the destination? Unknown. Maybe it's a habitable world. Maybe it's a barren rock. You won't know until you arrive, and by then you've committed everything. The risk-reward calculation is so skewed, it's almost absurd. You're asking a civilization to invest enormous resources, send members of their society on a one-way trip lasting generations, all for the chance that maybe, possibly, they'll find something worthwhile at the other end. Would you do it? Would humanity? Some individuals might. Sure. Pioneers, adventurers, those with nothing to lose. But would governments, corporations, civilizations allocate the resources needed for such missions? History suggests no. We went to the moon 6 times between 1969 and 1972, and then we stopped. Not because it was impossible. We'd proven it was possible, but because it was expensive, dangerous, and the scientific and political returns didn't justify continued investment. Mars is right there, 6 months away with current technology. We could send humans. The technology exists, but we haven't, because the cost is high, the risks are significant, and the questions remain. What do we gain? What's the return on investment? If we're hesitant to send people to Mars 6 months away, how much more hesitant would we be to send them to Proxima Centauri, decades away? How much more for distant stars, centuries away? And we're talking about us, a young civilization still fired with exploratory zeal, still curious about our cosmic neighborhood. An older civilization, one that's been around for millions of years, might have different priorities: stability, sustainability, risk aversion. They might have learned the hard way that bold ventures often end in disaster, that the universe is dangerous and unforgiving, that the smart move is to stay home, develop your local resources, build a robust and resilient society, and watch the cosmos from afar. This is called the sustainability filter. The idea that civilizations which survive long-term are those that prioritize stability over expansion, those that avoid risky ventures like interstellar colonization, and as a result, the galaxy ends up full of old, cautious, homebound civilizations, none of whom travel because none of whom think it's worth the risk. It's a depressing thought in some ways. It suggests that wisdom and caution lead to stagnation, that the bold exploratory spirit we celebrate might be a juvenile phase, outgrown by civilizations that survive long enough to learn better. But it might also be the truth. Survival is hard. The universe is hostile. Species go extinct. Civilizations collapse. Maybe the ones that make it, the ones that last millions of years, are the careful ones, the ones that don't take unnecessary risks. And interstellar travel is the definition of an unnecessary risk if you think about it coldly. Your solar system has everything you need: energy from your star, raw materials in asteroids and moons, living space if you build habitats. Even without Earth-like planets, you can construct O'Neill cylinders, rotating space stations that simulate gravity and provide comfortable environments. Our solar system could support trillions of humans if we built the infrastructure. Trillions. Without ever leaving, without ever needing another star system. Just clever engineering and patient development of local resources. Why risk the void when you have plenty right here? That logic applies to any solar system, any civilization. Stay home, build up, go wide within your own neighborhood, not deep into the galaxy. And if every civilization reaches that conclusion, the result is exactly what we observe. A galaxy full of life, potentially, but no interstellar travel, no visits, no contact. Just islands of intelligence scattered across the void, each one focused inward, on their own survival and prosperity. There's a related concept called the transcension hypothesis, the idea that sufficiently advanced civilizations don't expand outward into space. They expand inward into complexity. They build smaller, more efficient, more densely packed computational systems. They upload themselves into virtual realities. They manipulate matter at the atomic or subatomic level, rather than building megastructures. From the outside, such a civilization might be nearly invisible. Their energy footprint would shrink. Their signals would be minimal. They'd be there, but you'd never know it unless you looked very carefully. This is speculative, obviously. We have no evidence of post-biological civilizations living in simulated realities, but the logic is sound. Information processing becomes more efficient as you miniaturize. A civilization that values knowledge, computation, experience might find it more rewarding to build sophisticated virtual worlds than to colonize physical planets. And if that's the path most civilizations take, it explains both the Fermi paradox and the absence of visitors. They're out there, but they're not expanding. They're not broadcasting. They're not traveling. They're focused on internal development, on experiences and computations we can't even imagine, in substrates we wouldn't recognize. From our perspective, they've disappeared. But from their perspective, they've transcended, moved beyond the need for physical expansion into a realm of pure information and experience. Again, speculative, but possible. And if true, it means we might be surrounded by advanced civilizations we simply can't detect because they're operating on principles and scales we haven't conceived of. Now let's bring this back to Earth, to us, to the question that started all of this. Why haven't aliens visited? We've explored the physical barriers, distance, energy, speed limits, time, debris, radiation, navigation. Each one alone is daunting. Together, they form a nearly impenetrable wall. We've discussed the practical barriers, cost, risk, uncertainty, motivation, the lack of clear benefit for such enormous investment. We've considered the probabilistic barriers, the rarity of intelligence, the brief windows of detectability, the temporal coordination problem, the vast empty spaces between civilizations, and we've touched on the sociological barriers, the dark forest hypothesis, the sustainability filter, the transcension hypothesis. Reasons civilizations might choose not to travel even if they could. Each of these is a potential explanation, but together they form a comprehensive answer. Aliens haven't visited Earth because the universe makes it functionally impossible. Not just hard, not just expensive, but so overwhelmingly difficult on so many levels that even advanced civilizations don't attempt it. The walls are too high, the costs too great, the timescales too long, the risks too severe, the uncertainties too profound, and maybe, just maybe, that's okay. Maybe the universe is supposed to be this way. Maybe the vast distances and impossible barriers serve a purpose. They protect young civilizations like ours, giving us time to grow, to mature, to figure ourselves out without interference from outside. They give us space, literally. A cosmic quarantine where we can make our mistakes, have our conflicts, develop our technology and culture without the complications that contact with an alien civilization would bring. Think about what contact would actually mean. If aliens showed up tomorrow, it would fundamentally alter human civilization, our religions, our philosophies, our sense of identity. We'd no longer be alone. We'd no longer be the center of our own story. We'd be one species among many, and likely not the most advanced. That kind of revelation could be devastating or uplifting. We don't know, but it would certainly be disruptive. Maybe the universe, in its vastness, protects us from that disruption until we're ready, until we've developed enough, matured enough to handle it. Of course, the universe isn't conscious. It doesn't make decisions. But the laws of physics create a structure that has this effect nonetheless. Whether by design or accident, we're given time and space to grow up. And maybe that's the real message here. Not that we're alone, but that we're independent. Each civilization, each spark of intelligence in the cosmos, is fundamentally on its own. We can wonder about others. We can search for signals. We can dream of contact. But in practical terms, we're isolated. That isolation means our future is up to us. We can't wait for advanced aliens to solve our problems. We can't hope for rescue from climate change or war or existential risks. We're alone with our challenges, and we have to face them ourselves. It's a heavy responsibility, but it's also empowering. Our survival, our prosperity, our future among the stars depends on choices we make, not on luck, not on divine intervention, not on alien benefactors, just us. And that brings us to another profound realization. If interstellar travel is effectively impossible, if every civilization is bound to its home solar system, then what we do here matters immensely. Earth isn't just one planet among countless others we might colonize someday. It's our home, possibly our only home, for as long as our species exists. Mars might become a backup, a refuge, a second branch of human civilization. The asteroid belt might be mined. Europa and Enceladus might harbor colonies under their ice. But leaving the solar system? Traveling to other stars? Based on everything we've discussed, that's science fiction. A dream that physics doesn't allow, or at least makes so impractical that it might as well be impossible. So we need to take care of what we have. This planet, this solar system, this one chance at existence in a universe that's vast, beautiful, and ultimately isolating. That doesn't mean giving up on dreams of exploration. We should absolutely continue studying the cosmos, building better telescopes, searching for signs of life on exoplanets, listening for signals from other civilizations, sending probes to the outer reaches of our solar system and beyond. Projects like Breakthrough Starshot, which aims to send tiny light sail probes to Alpha Centauri at 20% light speed, are worth pursuing. Even if they take decades to arrive, even if they can only send back a few images before their power runs out, they represent humanity reaching beyond our immediate neighborhood. But we should be realistic about what's achievable. Sending humans to other stars, establishing colonies, creating an interstellar civilization, those are probably beyond us. Not because we lack ambition or creativity, but because the universe simply doesn't permit it. And you know what? There's something beautiful in that limitation. It focuses us. It reminds us that we're not separate from the universe, not exempt from its rules. We're part of it. Made of stardust, yes, but bound by the same laws that govern stars and galaxies. Our atoms were forged in the hearts of dying stars. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it created in stellar furnaces billions of years ago. We are, quite literally, the universe experiencing itself, looking back at itself, wondering about itself. And if we're isolated, if we're alone or nearly alone, that makes our existence even more precious. We might be one of the very few places where the universe has become conscious of itself, where matter has organized into patterns complex enough to think, to feel, to wonder. That's extraordinary. That's worth protecting. That's worth celebrating. The fact that aliens can't easily reach us, and we can't easily reach them, doesn't diminish the wonder of existence. It amplifies it. Every civilization, every spark of consciousness is a rare and precious thing, a candle in the cosmic dark, burning briefly, brightly, and then gone. But while it burns, while we exist, we have the privilege of looking up at the stars and asking questions. Where did we come from? Are we alone? What's our place in all of this? And through science, through observation and calculation and imagination, we find answers. Not complete answers. Science never gives us complete answers, but better answers, more accurate answers, answers that move us closer to understanding the universe and our place in it. We've learned that the universe is 13.8 billion years old, that it started in a hot, dense state and has been expanding ever since. We've learned that stars are born in clouds of gas and dust, live for millions or billions of years, and die in spectacular explosions that seed space with heavy elements. We've learned that planets are common, that most stars have them, that some of those planets are in the habitable zone where liquid water can exist. We've detected thousands of exoplanets, some rocky like Earth, some with atmospheres, some possibly harboring life. We've learned that the building blocks of life, organic molecules like amino acids and sugars, form naturally in space. They're found in meteorites, in comets, in the clouds between stars. Life's ingredients are everywhere. We've learned that life on Earth emerged quickly, geologically speaking, within a few 100 million years of the planet cooling enough to have liquid water. That suggests life might be common wherever conditions allow it. But we've also learned that intelligence might be rare, that the path from single cells to complex organisms to tool-using, language-speaking, technology-building civilizations is long and contingent, full of bottlenecks and lucky breaks. Earth's history is full of near misses, asteroid impacts that nearly sterilized the planet, ice ages that nearly froze everything, volcanic eruptions that nearly choked out the atmosphere. We made it through. But how many other worlds didn't? And even if intelligence arises, how long does it last? We've had technology for a century. We've had nuclear weapons for 80 years. We've been capable of destroying ourselves for most of our technological existence. Will we make it another century? Another 1,000 years? Another million? Nobody knows. But the fact that we haven't detected anyone else, haven't seen evidence of galaxy-spanning civilizations, or megastructures or Dyson spheres, suggests that longevity might be rare too. Maybe civilizations typically destroy themselves. Maybe they exhaust their resources, pollute their worlds, fall into wars, succumb to existential risks. Maybe the filters aren't behind us. Maybe they're ahead. That's a sobering thought. But it's also motivating. Because if the filters are ahead, then our survival isn't guaranteed. It depends on choices, on wisdom, on cooperation and foresight, and the ability to think long-term. We need to address climate change. We need to prevent nuclear war. We need to develop artificial intelligence carefully, ensuring it remains aligned with human values. We need to protect biodiversity, maintain our ecosystems, build sustainable economies. These aren't abstract political issues. They're survival issues. The universe isn't going to save us. Aliens aren't coming to fix our problems. We're alone with our challenges and we have to face them. But we're also alone with our triumphs. Every piece of art, every scientific discovery, every act of kindness and courage, those are ours, humanity's, the product of billions of years of cosmic evolution, culminating in this brief moment where conscious beings walk the surface of a small blue planet and wonder about their place in the vastness. When you look up at the night sky, you're looking back in time. The light from distant stars left them years, decades, centuries ago. Some of those stars might not even exist anymore. They might have died, collapsed, exploded, and we won't know for years because their light is still traveling toward us. The Andromeda Galaxy, that fuzzy patch visible to the naked eye on dark nights, is 2.5 million light-years away. The photons entering your eye left Andromeda when our ancestors were Australopithecus, early hominids taking their first tentative steps toward humanity. Those photons traveled for 2.5 million years through the void to reach your retina, to be absorbed by cells and converted into electrical signals that your brain interprets as light. You're not just seeing Andromeda. You're connecting with the ancient past. You're part of a cosmic story that spans eons. And somewhere out there, maybe, some other being is looking back toward our galaxy, seeing the Milky Way as it was millions of years ago, wondering if anyone's there, wondering if they're alone. They can't reach us. We can't reach them. The distances are too vast, the timescales too long, the barriers too high. But we're connected nonetheless, by the same physics, the same chemistry, the same cosmic history. We're all made of stardust, all products of the same universe, all asking the same questions. And maybe that's enough. Maybe connection doesn't require physical presence. Maybe knowing that others might exist out there, wondering the same things, facing the same challenges, bound by the same cosmic rules, is its own form of contact. We send our signals into space, radio waves carrying messages, mathematical proofs, images of Earth. The Voyager probes carry golden records with sounds and pictures of our world. Pioneer plaques show our location in the galaxy. These aren't practical attempts at communication. By the time any of these signals or probes reach another civilization, thousands or millions of years will have passed. We'll be gone. They'll be receiving messages from ghosts, from a civilization that existed long ago. But we send them anyway, because the act of reaching out, of saying, "We are here, we existed, we wondered about you," that matters. It's a message in a bottle thrown into an infinite ocean. We'll never know if anyone finds it, but we throw it anyway. And maybe, just maybe, we'll receive a message someday. A signal from another civilization, sent thousands of years ago, finally reaching our telescopes. We won't be able to respond in any meaningful way. The conversation would take millennia, but we'd know, we'd have confirmation. We're not alone. We never were. That knowledge would change everything. Not practically, but philosophically, psychologically. We'd know that intelligence can survive, that civilizations can persist long enough to send messages across the void, that we're part of a community even if that community can never physically meet. Until then, we're left with questions. The universe offers us mysteries, not answers. It challenges us to think bigger, to calculate carefully, to test our assumptions against reality. And reality tells us that interstellar travel is hard. So hard it's effectively impossible for biological beings with current or near-future technology. The energy requirements are astronomical. The timescales are longer than civilizations. The risks are severe. The distances are vast beyond comprehension. Light speed isn't just fast, it's the cosmic speed limit. And even at that speed, crossing the galaxy takes 100,000 years. There are no shortcuts, no wormholes we can access, no warp drives we can build with known physics. Time dilation means that even if you could travel at relativistic speeds, you'd be jumping into the future. Everyone you knew would age and die while you remained young. You could never go home. Not really. The home you left would be gone, replaced by a world decades or centuries older. The energy needed to accelerate even a small ship to a significant fraction of light speed equals the output of nations, or planets, or stars, depending on the mass and target velocity. Where does that energy come from? How do you generate it? Store it? Use it without destroying your ship? Debris at relativistic speeds becomes weapons. A grain of sand hits with the force of a bomb. Space isn't empty. It's full of particles, atoms, dust. At high speeds, they're deadly. Shielding helps, but perfect shielding is impossible. Something gets through. Gradually, inevitably, it damages your ship. Radiation in space is constant and dangerous. Cosmic rays, solar particles, gamma rays from distant explosions. On Earth, we're protected by our magnetic field and atmosphere. In space, you're exposed. Long-term exposure causes cancer, damages DNA, degrades electronics. Shielding is heavy. Mass you have to accelerate. Mass that requires more energy. Navigation at interstellar distances requires precision we've never achieved. You're aiming for a target light years away, moving at relativistic speeds. A fraction of a degree error means you miss by light years. How do you correct? How do you even know you're off course until it's too late? And motivation. Why go? Why invest unimaginable resources in a journey that takes generations, whose outcome is uncertain, whose success can't be verified for decades or centuries? What's the return on investment? What do you gain that you couldn't achieve by developing your own solar system? These aren't just obstacles, They're walls, built into the fabric of reality itself. They don't care about your technology level or your determination. They apply equally to everyone, everywhere, always. So when we ask, where are the aliens? The answer might simply be, at home, stuck in their solar systems just like we're stuck in ours, looking out at the stars with wonder and longing, but unable to bridge the gap. The universe is full of life, perhaps. Maybe intelligence is common. Maybe thousands or millions of civilizations exist in our galaxy right now, but they can't reach us. We can't reach them. The ocean between our islands is too vast to cross, and so we remain alone, not because we're special or unique, but because the universe is structured in a way that isolates us, that gives each civilization its own space, its own time, its own journey. It's a lonely picture, in some ways, but it's also honest. It's what the physics tells us. It's what the math shows. It's what reality looks like when you strip away wishful thinking and science fiction fantasies. We're not going to meet aliens anytime soon. They're not going to visit us. No flying saucers, no first contact, no benevolent space brothers arriving to solve our problems or malevolent invaders arriving to conquer us. We're on our own, in a universe that's vast, ancient, beautiful, and fundamentally isolating. But that's okay, because we have each other. We have this planet. We have this moment in cosmic history where we get to be alive, to think, to wonder, to explore. We've sent probes to every planet in our solar system. We've landed rovers on Mars. We've flown past Pluto. We've detected thousands of exoplanets. We've captured images of black holes. We've observed gravitational waves from colliding neutron stars. We've done all of this in less than a century of spaceflight. Imagine what we might achieve in the next century, in the next 1,000 years, in the next million, if we survive that long. We might not reach other stars, but we can still explore. We can still discover. We can still push the boundaries of knowledge and understanding. We can build telescopes that peer deeper into space and further back in time. We can search for biosignatures on exoplanets, looking for oxygen, methane, phosphine, signs that life exists elsewhere even if we can't visit it. We can develop our own solar system, colonize Mars, build habitats on the moon, mine asteroids, establish research stations on the moons of Jupiter and Saturn, create a spacefaring civilization that spans our local neighborhood. We can ensure our survival, address the existential risks, build a sustainable civilization that lasts not just centuries but millennia, millions of years, long enough to become one of the old ones, the ancient civilizations that persist while others rise and fall. And we can keep looking, keep listening, keep wondering. Because even if we never meet aliens, the search itself is worthwhile. It tells us about the universe. It tells us about ourselves. Every negative result from SETI, every exoplanet we study that shows no signs of life, every star system we examine that contains no megastructures, tells us something. It refines our understanding. It constrains the possibilities. It helps us answer the question, are we alone? We don't have the answer yet. Maybe we never will, but we're asking the question. And that, in itself, is remarkable. So here we are, on a small rocky planet orbiting an average star in the outer suburbs of a spiral galaxy. One planet among billions, one star among hundreds of billions, one galaxy among trillions. Tiny, insignificant on cosmic scales, and yet significant in our own way, because we're the universe looking back at itself. We're matter that has become conscious. Atoms arranged in patterns complex enough to wonder where they came from and where they're going. The aliens, if they exist, face the same barriers we do. They're bound by the same physics, limited by the same constraints, isolated by the same vast distances. They can't reach us. We can't reach them. The universe keeps us apart. But we exist nonetheless. We think, we wonder, we explore, and in doing so, we give meaning to the cosmos. We're the universe's way of knowing itself. And that's enough. That has to be enough, because it's all we have, and it's everything. If you found this deep dive into the physics of interstellar travel fascinating, make sure to hit that subscribe button and give this video a thumbs up. And if you're curious about the challenges of space exploration closer to home, check out the video on the screen. Why the first humans on Mars will be trapped there forever. You'll discover why the red planet might become a one-way destination for humanity's first interplanetary pioneers.